All right. Hello, everyone, and thank you so much for joining us today for this week's session of the Parks College Weekly Webinar Series. My name is Amy Price, and I'm the Outreach Coordinator here at Parks College. I'm joined today virtually by Dr. Kyle Mitchell, who will be showing us around the Center for Sensors and Sensor Systems. We are very excited to have you joining us today from wherever you are. Thank you for taking the time to virtually visit and learn more about the computer engineering program at St. Louis University. In total, Parks College has programs available in aerospace, biomedical, civil, computer, electrical, and mechanical engineering, as well as flight science and aviation management and engineering physics. We hope that today you will hear or see something that interests you. Before we start, I want to give you an idea of how the webinar will flow. I will soon introduce Dr. Mitchell, who will be showing you around the lab space and sharing information about computer engineering. He then will hopefully introduce Park student Joe Sloyan. He'll be logging in a little bit later, and he will share his experience of being an engineering student with you. And finally, we will conclude with time for questions and answers. Throughout the webinar, please submit any questions you may have to the Q&A feature at the bottom of your screen if you're viewing through Zoom, or in the comments section if you're viewing through Facebook Live. And we will do our best to answer as many questions as possible during the last 5 to 10 minutes of our session. Throughout this webinar, you don't need to worry about turning off your microphone or camera. You can hear and see our presenters throughout the webinar, but we cannot hear or see you. Finally, if you have any technical difficulties during the webinar, please email parksevents@slu.edu and we'll help to address any issues that may arise. This session will be recorded and posted to our YouTube page in the next day or two, and you'll receive an email with that link when it becomes available. And now, with all of that housekeeping out of the way, I am very happy to introduce Dr. Mitchell and the Center for Sensors and Sensor Systems. So, Dr. Mitchell, I will turn it over to you now.
Thank you, Amy. Like Amy said, my name's Dr. Mitchell. I work here in the Center for Sensors and Sensor Systems. That's a big word. It's a small space, but a big word. So what we do in this lab is we work in two areas. One of the areas is referred to as embedded system design, and the other area is referred to as signal processing. So embedded system design, that's a fancy word that basically means we build computers. We build computers that have very different functionality than you may be used to, because we build computers that go places that humans typically don't. So we build the computers that go inside your television. We build the computers that go inside your microwave. We build the computers that go inside your car. Now we build things for a very special purpose, and that is that we want to collect sensor data. So we build computers that specialize in having sensors attached to them, and then being able to store the sensor values someplace. That someplace can be on a local storage, that someplace can be transmitted wirelessly to a remote storage site, that someplace can be in the cloud. Most of the stuff we do, since it's just data that we're collecting for our own consumption, is we build computers to store things locally. Now, throughout the presentation today, I'm going to show you what some of these computers might look like. I'm going to show you some of them in action, and we're going to talk about what some of the sensors that we integrate into these systems are and how they function. The other half of the lab is the signal processing half of the lab. So signal processing is an area of electrical engineering that's concerned with using the math of calculus and differential equations to produce information from data. So in signal processing, we run a lot of different algorithms, filtering type algorithms, and separating type algorithms, and quantification algorithms, so that we can look at data sets that come from these sensors that I build systems to collect raw data from, and we do that processing to collect information. So raw data is typically pretty difficult to determine, if there's anything useful in it. That's what the signal processing comes into play. So the signal processing tells us if the attribute we're looking for is present in the data. And I'll try to explain what some of that means in specific terms as we move through here. So the embedded systems that I design, this is an example of one. Like I said, we're going to look at several of these along the ways. This is not one that I designed. That's just an example of what an embedded system might look like. Notice that this really doesn't have a keyboard, really doesn't have a mouse. It has very specific I/O ports on it. And like I said, these things exist in most of our modern devices. Your watch probably has one in it. Some people's shoes have them in it. Your refrigerator has one in it. Your car has 12 of them in it. These things are really everywhere. And these are the devices that really make the modern part of modern devices work correctly. All right, with that being said, let's go look at one of these things in action. So I'm going to show you an experiment that we're presently running, and we're going to talk about some of the stuff that's going on here. So this particular experiment we're running, we do a lot of work with the other labs on campus. So this is a lab that specializes in designing autopilots for remotely piloted and autopiloted aircraft. So this is the tail section off of one of the drones that we build here in-house. This is on a shake table. So if you look at the instrument in the bottom right-hand corner, the yellow line across the bottom is the frequency that's being driven from the blue shaker. The green line on that, and we'll look at this in a little bit better resolution here in a second. The green line is how far up and down the tail is actually moving. What we're looking at in this experiment is what happens to this tail when it gets put into resonance. So resonance is a feature that mechanical structures have that if you put energy in at a certain frequency, the structural makeup of the structure will amplify that energy. So the energy we're putting in here is exactly the same all the way across the frequency range. And the frequencies that we're putting in here are someplace between 4 and 7 hertz. So that's what the yellow line represents, is a sweep between 4 and 7 hertz. But someplace around 5.5 hertz, we find one of these resonance of this tail. And that's why you see the tail move a little bit at the low frequencies. It goes through a period where it shakes a lot, and then you see it go back to not shaking very much. So that's the phenomenon we're studying. But what we're studying with that phenomenon is what happens to the internal forces of the structure. So I'm going to change screens here. So there's a expanded view of what was on the scope there. So notice that the amplitude of the energy that we're putting into that shaker is constant across the yellow, but the displacement that the tail undergoes varies with frequency. So what we have helped Dr. Guru Rajman's lab do is we have helped them measure the internal forces that are at play inside of that structure. So that structure has 10 strain gauges on it. A strain gauge is a sensor element that is able to measure how much a solid stretches or compresses. Right. So the picture on the left here is a board that we developed in the center that is capable of measuring 8 strain gauges and recording the data from those strain gauges at 1,000 samples per second. All right, there's 2 boards in this stack, so we're basically recording 16,000 samples per second of compression data from that tail section as it goes through this shake. The ultimate goal is that we want to be able to build these and fly them around in craft. You're going to see several of the examples that I talk about today are about flying these sensors inside of craft in the air, with the ultimate goal being we are working on designing a more intelligent autopilot for small craft. All right. So this particular board, it reads changes in those resistors. So a strain gauge resistor, a nominal strain gauge resistor is about 220 ohms, and we're measuring changes in resistance at about the 10 micro ohm level. All right, so we're measuring changes in resistance someplace around the 1 part in 10 million change. That's a really small number to measure. So we're measuring stuff in the 7th significant digit. And the little black chips on this board do all of that for us. So these are strain gauge amplifiers. So you know, what the center did was we put some filtering circuits together. We selected the amplifier, we programmed this so that it could interrogate the sensors, and then we programmed it so that it would store that data. One of the other things that we have gotten relatively good at is you'll notice that there's two of these boards. Those two boards store their data so that it's time synchronized. And we'll talk about time synchronization here a little bit later. So let's go ahead and look at another one of the projects that we're working on with Dr. Guru Rajman. This is a HEX rotorcraft. Most of you would recognize this as a moderate lift drone. These things are really, really fun to fly. They're really fun to watch being flown. They're not very much fun when something goes wrong with them. And the reason they're not very much fun when something goes wrong with them is the autopilots in them assume that the structure of the craft is static. So if you get a crack in the craft someplace, or you get one of the propellers to become delaminated, or one of your motors starts to develop a bearing problem, the craft no longer acts the way it was designed, and the autopilots really struggle to deal with that. So the work we're doing is we're instrumenting craft like this and like the previous craft so that we can detect when something is changing in the craft, tell the autopilot that we've seen something change, and then another group is working on how do we make the autopilots so that they can learn what has changed and continue to operate inside a set of normal parameters for the craft. So this particular structure, the little red sensor, if you look real close at the picture on the left, you'll see that there's one of those attached to each arm. These sensors have what's called an inertial measurement unit, an IMU. So these are 6-axis IMUs. What these things can measure is they can measure acceleration in the X, Y, and Z direction. So they can tell us if this thing if the motion direction or velocity is changing in the X, Y, and Z. And they can measure pitch in the X, Y, and Z, or actually roll in the X, Y, and Z. Their gyroscope. So what that allows us to do is determine, are they spinning? So is the arm moving X, Y, or Z, and is it rolling X, Y, or Z? And as the craft flies, we should expect some of that to happen because the craft is moving around, it's changing directions, it's changing angles. But you'll find that the motors give off certain vibrations. And if we watch those vibrations, we can actually watch the dynamics of the craft change as we damage the craft. So what we do is we fly this thing with damaged propellers, we fly this thing with cracked arms, we fly this thing with more weight in places and less weight in places, and we watch how the roll, pitch, yaw, and XYZ translation change. And by using signal processing on those, we can determine that the craft has changed. We can put that information into the autopilot, and the autopilots can then do something to account for the fact that the dynamics of the craft have changed. All right, another one that we're doing very similar work with. This is the full version. The wings don't fit because it doesn't fit in our lab that way, so they're on the floor next to it. But this is the full version of that craft that we saw the tail section shaking of. This one we actually take out to Booter Park here in St. Louis and fly. It has another board on it that was developed in the center. This particular board records slightly different things. So the big white box is another IMU. So again, we're measuring roll, pitch, yaw, and XYZ accelerations. But we're also recording the data that the pilot is putting in here. So as the pilot moves the remote control around, we're recording where the remote control sticks are pointed. We're recording the GPS coordinates of this. We're recording the altitude of the device through an air pressure device or an air pressure sensor. And we're recording the air speed of this airplane. Again, this airplane is meant so that we can gather data in an effort to build better autopilots. So what we do with this airplane is we induce fault. We can make it so that certain control surfaces don't work correctly. We can make it so that the engine doesn't respond correctly. Sometimes we will replace wings with physically damaged sections. And what we're trying to do is record what the pilot does in response to the changes in the aircraft. Because if we can understand what a good pilot does in response to the changes in an aircraft, that can point us in a direction for where we should go with what an autopilot should do when the sensors we've put on board detect a change in the aircraft. So we're using what humans have been doing for several decades as a training tool for what we want our computers to do into the future. A couple other historic things we've done. I said that we work with other laboratories. So if you look at the board on the right here, this particular board is one that we developed in the lab to fly on the first spacecraft that SLU launched. So I know that some of you saw Dr. Swartout's presentation from the Space Lab a couple weeks ago. This is a ground representation of the board that actually flew on one of those crafts. So this board's job was to take infrared images and store them locally. So this is kind of a fancy camera, only it's a fancy camera that operates in the infrared. Its secondary job was to interact with the radio so that when the ground asked the spacecraft for certain pictures, this board would serialize that data and send it back to the ground. So we do a little work with a lot of people. Let's go back to looking at another demo. So I'm going to show you kind of a live demo at this point. So in our lab, we develop the ability to do different things on the web. So on the table behind me is a articulated robotic arm. This arm is a demonstration project for a number of different experiments. The first of which is we teach students how to build web pages and build embedded systems. So if you look around the table there's a little embedded system right here. The blackboard that's actually controlling all the motors. There's another one that's just off camera that we didn't design. It's a Raspberry Pi. We do use commercial computing platforms to do certain things, but this Pi has been programmed to serve this web page, to produce these inputs, and to respond to remote user rather than local user inputs. So what I'm going to do is I'm going to drive this robot through a series of motions, just so that you get an idea of what it might be like. And as I'm doing that, I'm going to talk about additional things. So along with teaching people how to put things on the web, put experiments on the web, put data collection on the web, we also use this in robotics classes to teach people things about what's called forward kinematics and inverse kinematics. So forward kinematics and inverse kinematics are, you notice that I'm going to put a bunch of angles into these fields. Well, using certain mathematical structures, you can predict the final position of that robot if you know the length of the arms and the angles that are put in. That's kinematics. The other thing, you'll notice that I did not drive this robot to its final position in one step. I did not drive it to its final position in one step because it would have knocked the little white block I'm trying to pick up over had I done that. So we also teach something called path planning. So as your robot moves around its environment, you have to plan on it not running into its own environment. So that's what path planning is all about, and that's another thing that we use this robot to study. All right, so let me finish my path here. $250 minus 400 minus. So each one of these are, like I said, they're angles, but they're angles in tenths of a degree. So I'm moving it to minus 45 degrees, 25 degrees, minus 40 degrees, minus 50 degrees, and then a pinch of minus 120. All right, you notice as it went through that path, it almost ran into the ground. It took me a number of tries to develop this path to keep it from running into the ground. And I'm going to now set the block down. If I don't, well, we will. Let me go to the final position and see what happens here. we don't usually do this by hand. This is just a training mechanism. We usually do this, we program this together and we let the computer do this for us. All right, so there it's on the ground. I can release it. And then if I pick the right joint, I can pick the robot up away from it. And I didn't quite pick the right joint, but that's okay. So that's some of the stuff we do that's not quite sensor related, but related to the rest of the stuff. I'm going to introduce my student at this point. I have a couple more of these we can talk about if we have time at the end. But I noticed that Joe has joined the conversation. So let me introduce Joe and have him say a few things to you.
Hi, can you guys hear me okay? Am I good volume-wise?
You're good.
Great. My name is Joe Sloyan. I am a senior computer engineering student. I am from Downers Grove, Illinois. I have been at Parks College now for 3 years. Sorry, I don't have the questions that you want me to answer in front of me here.
So talk to you about what you've done in the lab and what excited you and why did you come to work in the lab?
Sure. So I have been now for about a year working with Dr. Mitchell in his research lab. It really kind of started when I wanted some kind of outside projects to do, just some more things for me to, kind of do on my own, kind of keep me engaged in a couple, more interesting things that were real world problems. So I asked Dr. Mitchell if he needed help. So he's got a bunch of different things for me to do. So I've been working on some work for the NGA and developing something called a zero client for them. I've done some work with robotics. I've done some work with fixing old senior design projects. It's been a good time.
So, what brought you to Parks? What excited you about SLU?
So I had a pretty narrow criteria for what I wanted going into college. So from high school, I knew I wanted to go to a school in a city. I knew I wanted to do computer engineering, and I knew I wanted about a medium-sized school. So there were, a couple, different things I looked around for. I had a small list. I toured each of them. I found that I enjoyed my tour here the most. But since I have come here, a couple things that I found that were just pretty much happy coincidences that I didn't really know about before I came here, but ended up being big pluses, is the relatively small class size. I know all of my classmates very well in pretty much all of my classes. I'm friends with almost all of my classmates in every single class I'm in, which is great because we do, outside study groups. We'll have, a lot of times we'll do a little like an ECE get together or something outside of class. I also know all the teachers fairly well and they all know me. So, I have decent relationships with all the teachers and they all know, who I am and I can approach them and get help from them. And they're, willing to be flexible a lot of the times if, I need extra work with something. So that's the big advantage that I would say.
Great. All right, I think Amy's cutting back in now at this point.
I want to make sure that we had some questions come in and I want to make sure we get a chance to answer them. So first, this is more for Dr. Mitchell, but Joe, you might have also worked on this project. But Dr. Mitchell, when you were showing the example of the autopilot inputs on the airframe deflection test, there's a question asking what would happen if the frequency weren't constant. So you're testing it with a constant frequency of movement, but what would happen if it were variable?
So the frequency I'm testing with it is variable. So let me talk about that on both sides. So I'm sending it, and I can show that here. I'm sending it a sine wave that changes between 4 hertz and 7 hertz. Give me a second here. All right, so if you look, it's slower at one end than it is the other. And that's why you see that it has a certain response, the response changes, and then the response goes back down. If we put just a constant frequency in, then the response, the tail would just shake all the time or not shake all the time. The fact that I'm putting the variable frequency in is why it goes through periods of not shaking and then periods of shaking and then periods of not shaking again. So it's not quite the answer to your question, but that's where we're getting at. The thing that we really need to be careful about is we don't know what frequencies are going to be present when we're flying this thing around. Air is going to be running across the top of this, and the air will induce certain vibrations, but those vibrations will depend upon the speed the aircraft is running at. It will depend upon how the pilot is moving the joysticks. So the input to this system from natural forces will be constantly changing, and that's why we test it with changing inputs, the swept sine wave in specific.
Thank you. Thank you. That clarifies. Another question. These are great questions, guys. Keep them coming. What exactly do you build by hand in the lab? So within the computer system, some things you said you are purchased and then you just reprogram them, but are there circuit boards that are built by hand, or what are students and faculty doing in the lab space?
So it depends on the system we're chasing and whether it's available off the shelf or not. If we can buy stuff that's pretty close to what we need and we just have to reprogram it, that's what we do. But when you look at this particular project in general, the reason this board has our name on it is we sit down with pencil and paper and we lay out a circuit. We take that drawing or that thought of what the circuit needs to be, and we go into a CAD tool called a printed circuit board layout. We draw this. So every place that there is little copper traces on this circuit board and every place there's footprints for chips, we actually draw this the same way you would draw a mechanical drawing or an architectural drawing. So we go into a CAD tool, we draw this. We send that drawing to a fabrication facility that prints this board for us. So printing this board is an environmentally dangerous process. So we let other people that are better prepared to take care of the environmental concerns, because you're producing copper chloride when you do this. So they mail this back to us. When they mail it back to us, it's just a plain green board. It doesn't have anything on it. So we in the center then come back and we solder all the connectors, solder all the chips, solder all the resistors onto this. We plug all the wires in, we turn it on and see what it is. So again, it depends a lot, but we do everything from, the satellite board that I showed you was a board that we designed in-house and soldered in-house, to, I talked about the robot arm where the Raspberry Pi was capable of doing what we needed to do. So we just used the commercially available thing. We do a lot of looking at what people need, seeing if there are things that are available for that, and if there aren't, designing them custom.
Gotcha. Thank you. Thank you. I think we have time for just one more question. So I'm going to ask it in a different way to both of you. So Dr. Mitchell, what's the future of computer engineering? Where's the field heading? And Joe, does that dovetail with your career goals, or what are your career goals? What are you individually planning for yourself? So Dr. Mitchell, I'll let you go first.
So the future of computer engineering is headed in lots of different directions. The embedded systems that I deal with, this is the foundation of what is referred to in the community of the Internet of Things. So as we put more and more connected devices into the world, the embedded system environment is just growing by leaps and bounds. But computer engineering is much bigger than just embedded systems. We deal with information security, we deal with information storage, we deal with high performance computing, we deal with the things on your desktop. Computers are just going to become more and more pervasive. They're already everywhere. You carry 3 or 4 of them around with you, and that that idea will just continue to grow. Now, there are several facets to that. You can go into application development as a comp sci. You can go into hardware development as a computer engineer. You can do things that are someplace in the middle, and that's what I do as a computer or as an embedded system designer.
So I am more on the software side of things, as where Dr. Mitchell was kind of mentioning that there's both the software, hardware, and the kind of in the middle stuff. I do enjoy the systems designing, kind of in the middle stuff too, but I'm largely on the software side. I tend to enjoy like not exactly high performance programming, but certainly along the more making things efficient and the the problem solving side of things. So that's where I am. That's kind of where I look for career opportunities.
All right. Well, thank you. Unfortunately, I think we are out of time, but thank you for everyone who joined us today. And we hope that you enjoyed this virtual visit to the CSSS with Dr. Mitchell and with Joe. If you would like to learn more about the engineering programs at SLU, please visit slu.edu/parks. And as always, please reach out to us at parksevents@slu.edu if you'd like to connect further with us. Finally, please plan to join us again next week for another installment of our weekly webinar series on Friday, October 9th at 1 p.m. for a visit to a mechanical engineering program lab. So thank you once more for joining us, and have a great rest of your day.